Okay, well, hello everyone, and welcome to our podcast, PAIS, Root Causes, Drivers, and Actionable Solutions, in collaboration with Elsevier's The Raise the Line podcast. I'm your host, Dr. Raven Baxter. I'm a molecular biologist and director of science communication at CORE, the Cohen Center for Recovery from Complex Chronic Illness at the Icahn School of Medicine at Mount Sinai Hospital. At the center, we work to advance treatment and knowledge of long COVID, chronic Lyme, myalgic encephalomyelitis, chronic fatigue syndrome, and hypermobile Ehlers-Danlos syndrome. And today, we have a comprehensive discussion about the building blocks of post-acute infection syndromes with three distinguished guests I'm very excited to engage with today. We have Dr. Amy Proal, Dr. Akiko Iwasaki, and Dr. Ed Breischwert. Welcome all. I'm going to give a brief intro to you all so our audience knows how special and awesome your work is and who you are. So Amy Proal is a microbiologist, president and CEO of the Polybio Research Foundation. She's recognized for extensive work to understand microbial communities and their effects on human health. Her research delves into the complex interplay between chronic diseases and microbial infections. Dr. Akiko Iwasaki is an immunologist at Yale University, and she significantly advanced our understanding of the immune system's responses to viruses and vaccines, offering crucial insights for combating infectious diseases. And we also have Dr. Ed Breischwert, who's an expert in vector-borne diseases from the North Carolina State University. He's conducted groundbreaking research on the Bartonella species and has unveiled some of the roles of these pathogens in chronic illness. Welcome to everyone here. You represent a spectrum of expertise, and it's going to be very interesting to have this conversation about the building blocks of post-acute infection syndromes. So, for many of our listeners today, this may be the first time that they're ever hearing about post-acute infection syndromes, which is sort of hard to believe considering our world has been rocked by a pandemic caused by a virus, and really even prior to that, the role that acute infections play in our bodies has been largely uncovered for many medical students. And so I would love to just offer them a definition of what is a post-acute infection syndrome. Amy, do you want to kick this off?
Sure.
So I would love to offer a definition for the students listening. What would you define as post-acute infection syndrome?
Great, Raven. So for many decades now, we've understood that most bacterial, viral, and even some fungal pathogens are associated with a chronic condition or chronic syndrome that begins after acute infection. The patient becomes infected and then they develop debilitating chronic symptoms. Sometimes they could last for a lifetime that don't go away. And we call those post-acute infectious syndromes. They could be initiated by a viral infection, a bacterial infection, and like I said, sometimes a fungal infection. Long COVID is a prime example of a post-acute infectious syndrome, or PAIS. Obviously, most of us, unfortunately, have gotten infected with SARS-CoV-2 and suffered from the acute illness COVID-19. But a subset of patients, up to 6%, for example, of Americans, are developing chronic symptoms after COVID that don't go away. And those patients are getting diagnosed with long COVID, which is a post-acute infectious syndrome, or PAIS.
Thank you for that. And Ed and Akiko, do you have anything to offer as far as expanding on that definition at all?
I think we did a great job. I just want to emphasize that this type of PAIS have been known and documented over decades. However, really hasn't been studied well because many of these syndromes occur in small pockets, and it's difficult to study PAIS in totality when you have one or two people at a given time getting this PAIS in different locations. Whereas the long COVID has kind of provided us with a opportunity to study this disease in a concerted manner throughout the world. So this very important sequela of infection that really haven't been studied much until now.
It made me reflect on a lecture that I've given to veterinarians and physicians over a number of years that was persistent infection and complex disease expression. And one of the advantages I have on the veterinary medical side is that many of the organisms that are vector transmitted have to either be in a vector, the insect or the arthropod like a tick, or they have to be in a host. And therefore, from an evolutionary standpoint and from a biological standpoint, they're dependent on that host. And so it's not unusual for there to be an acute infection where the animal gets sick and then the immune system in the animal reach a state of balance, which is referred to in the literature as premonition. And then they kind of live together peacefully until something starts to go wrong, or the other alternative is it's not so peaceful and there's this constant deterioration in health.
Thank you for that. And I think that's a perfect opportunity to turn to Amy. You have done work on microbiomes. What is the intersection of microbiomes and PAIS?
That's a good question, Raven, and it still remains to be explored in a profound capacity. But it is at a baseline important to understand that every person is filled with trillions of interacting organisms. These ecosystems of organisms that are in many of our body sites are referred to as the human microbiome. The gut has the most robust microbiome ecosystem in the human body, but these communities of organisms are also present in the mouth and increasingly identified in other body sites. So what's important is that these ecosystems contain bacteria, they contain fungi, and they even contain viruses called bacteriophage that infect the bacteria and modulate their activity. And what that is a bit similar to is honestly a rainforest community, for example, where you have many different species of organisms all living together and interacting in ways in which their community interactions and balance are important for the overall health of the rainforest. That's occurring in the human body just with bacteria, fungi, and other organisms. And the key thing is that under conditions of health, those organisms are actually in a state of balance or homeostasis. But under conditions of immunosuppression or imbalance, those communities can sometimes shift collectively towards a state of imbalance or inflammation called dysbiosis. And one of many things that could potentially cause this shift towards dysbiosis is a new infection. So there's some research that suggests that, for example, if a person gets a viral infection, such as SARS-CoV-2, and that virus reaches the gut, these other ecosystems of organisms may also be impacted. For example, SARS-CoV-2 might downregulate the immune response. For example, it might downregulate the signaling of interferons, which are important molecules that keep other organisms in check. And that could allow this collective microbiome to shift towards a state of imbalance where it may begin to drive symptoms. And last, what's important to understand is that the microbiome, actually these organisms produce compounds that are important in human signaling pathways. So organisms in the microbiome, for example, produce tryptophan or other metabolites that can impact human signaling. So if their collective imbalance shifts to become problematic, many of our human pathways and the signaling that impacts chronic disease can be also impacted via those shifts.
That is absolutely fascinating. It's like a world inside of a world that we're talking about here. And so going on the line of bacteria, not all bacteria are the same. I'd love to hear from Ed your thoughts on Bartonella and its role in post-acute infection syndrome.
So our research with Bartonella actually started shortly after the bacteria was discovered for the first time in immunocompromised humans in North America as a result of another viral epidemic, and that was the HIV epidemic. And I think that's important and instructive in the context of us talking about occult infections, essentially those that, fly well under the radar, and chronic disease expression, because it's a fair and accurate statement that we did not know that a cat, dog, horse, veterinarian, or any other animal in the North American continent was infected with a Bartonella species. If we only use the cat as example, we know that they are reservoirs for 3 Bartonella species that are transmitted by fleas, And we know that cats have been infected, based on research around the world, with up to 5 or 6 Bartonella species. So we went from not knowing a genus existed to now knowing that, literally cats are a major reservoir for this. And almost everyone is familiar with cat scratch fever or cat scratch disease, where a scratch can result in the transmission of this bacteria to a human and induce an acute illness, which is cat scratch disease, but can also, after that acute illness in a subset of people that immunologically do not clear the bacteria, result in very chronic and very debilitating disease.
That is absolutely fascinating. Oh my goodness, thank you for sharing. And so, pivoting a little bit and diving into immunology, Dr. Iwasaki, how does your work in immunology intersect with our understanding of post-acute infection syndromes?
So prior to COVID, we've been working on immune response to multiple different viruses. We've worked on herpes simplex virus that causes, oral herpes and genital herpes, to Zika virus, to, currently SARS-CoV-2 infection. But throughout this, what we've been paying attention to is what is really the actual driver of diseases associated with infections. People assume that infectious diseases are caused by the actual agent itself, such as the virus is causing lytic infection and damaging organs. But oftentimes what it is the immune response against the virus that's either overexuberant or that is inappropriate, that then end up causing the disease itself. And that's borne out in the case of acute COVID infection, for example, that it's really the excessive myelopoiesis and stimulation of macrophages and blood clots and, excessive immune response that then led to lethal diseases. So with that in mind, we're looking at long COVID and PAIS in general with the lens that it's not the pathogen themselves that are necessarily causing the disease, but the chronicity as well as the immune response to these pathogens that are somehow inappropriate or dysregulated in a subset of people that then lead to these kinds of chronic conditions. And so, for instance, this type of dysregulated immune response could lead to persistent virus infection, which Amy and I are studying as well as many others, that could be causing some of these syndromes, whereas it could also be that it's the bystander autoreactive T cells and B cells that are stimulated and leading to autoimmune diseases that are not yet well characterized in people with long COVID. There could also be activation of other viruses. Just as Amy described microbiome, there is a whole world of virome, which is a collection of viruses that we harbor in a human, as well as in our genome, that may become reactivated after an acute infection with SARS-CoV-2. And that could also be causing symptoms. So no matter how you look at it, the immune system is integral to understanding these PAIS, whether it's because it's not helping clear the virus or whether it may be causing a dysregulated or even unwanted type of immune responses. And we're already seeing clear signatures of immune activation and exhaustion in a subset of people with long COVID.
Thank you. I would love to dive deeper into some of the theories behind the roots of these diseases. Can we start with persistent pathogens and what that is, how that occurs, and what the long-term implications are in the disease process?
Yeah, I think I'll let Amy talk about that since she's an expert.
Sure. It's actually a very straightforward mechanism, which is that the pathogen that initiated someone's symptoms does not fully clear, and again, for a number of reasons, may actually remain with the person. Key, though, is that the pathogen may not persist in a very easily identified form, for example, floating in the blood in very high numbers. What may happen, and what we're finding evidence for in some PAIS, is that the virus or infecting pathogen that persists actually sticks around in patient tissue or nerves in what we call a reservoir. So it's a small amount of the pathogen, low biomass that remains somewhat protected in tissue where potentially it's less likely to get targeted by the immune system in some capacities. There, though, even that small reservoir of the persisting pathogen in a person's tissue or potentially nerves could still drive disease or symptoms in a number of ways. For example, it could continue to provoke the immune response. It could actually potentially cause inflammation that could wear down nearby barriers. So, for example, one thing we look at is that the gut actually seems to be a site of reservoir for SARS-CoV-2 in some of the studies that we're finding now. And if that happens, perhaps inflammation from those reservoirs could wear down the lining of the gut, allowing it to become more permeable. That can then allow, whether it's protein created by the pathogen, like SARS-CoV-2 in the reservoir, or organisms in the microbiome, as I mentioned before, to leak into the blood where they can cause other problems, for example, clotting or immune activation there, potentially even blood vessel issues. So there's a lot of flow-on effects that can happen from these reservoirs. So that is really the main gist there, is that the person does not clear the infection, and yet it may not be simple to find these reservoirs in patients. And that's why part of when we're researching them now in patients with PAIS, we are not just getting blood samples from patients, we're also getting gut tissue samples, for example, from endoscopy procedures, or lung tissue samples via bronchoscopy procedures. There's even some teams doing lymph node biopsies, because the reservoirs or the persistent organisms may be in those tissue sites that are harder to access. So a takeaway from that for a clinician is that if a patient comes into your office with a PAIS, like long COVID, their blood might still seem okay. And for example, with SARS-CoV-2, they'll still test negative for the virus on that standard nasal swab test that we use in acute illness. But it's possible that they might still harbor a reservoir of SARS-CoV-2 in the tissue of their gut or something like that. So further investigation is required, and we can't really rule it out on an average clinical visit.
And would you say that the tests for that are still developing? Like, we're still trying to find ways to find the reservoirs and get samples?
Absolutely. Yes, that's one of the things that is a big area of interest and momentum in the fields of PAIS right now. In some sense, if there's a reservoir of the pathogen in tissue, perhaps some of the protein that's still being made by that pathogen could leak into the blood where it could be measured. So there are some groups that are trying to work on tools to find small amounts of pathogen proteins in blood. You could also use, and Akiko could speak to this, antibody responses to try to infer, even from the activity of cells from the innate immune system, or even the activity of T and B cells that circulate through the tissues, to be able to understand that those cells might be in a state where they still seem like they're responding to persistent pathogens or persistent antigens or proteins created by those pathogens. But that does require more technology development than what exists now, especially in the clinic. And so it's an ongoing area of exploration.
Thank you. Question about the gut. Is the gut an ideal place for a virus to hide out, or are there other places in our bodies that are natural reservoirs for viruses?
The gut is, for SARS-CoV-2, a very likely reservoir site for a few reasons. It's one of the areas that most expresses the ACE2 receptor that the virus uses for entry into cells. So those cells are very dense and making it a nice atmosphere for infection of the tissue of the intestinal lining. Also, the virus, in this case in long COVID, SARS-CoV-2 reaches the gut in a good number of patients. We now understand that the virus often moves into the gut and drives GI symptoms. So it's a place where it ends up in a lot of people. Also, the gut is a reservoir site for HIV. It's a known site for other viruses. So there's some context from other pathogens that gut is a likely reservoir location. That doesn't mean, though, that it's the only reservoir site by any means. I think another place that's interesting to think about with certain viruses and actually bacterial pathogens are nerves. So nerves, especially the herpes viruses, and again, herpes viruses remain with us for life. So once you're infected with Epstein-Barr virus or another herpes virus, you actually carry that virus for a lifetime. And those viruses are neurotrophic, which means that they preferentially infect nerves. So if you're going to find that virus and connect it to a disease process, it might be doing something in a nerve. And one of the nerves we're interested in as a reservoir, as a persistent infection site for certain pathogens is actually the vagus nerve, which is a nerve that traverses the body, innervates every major trunk organ, and connects to the brain. And that could lead to a wide number of symptoms if that nerve remained infected in any capacity. So I think that other sites in brain and nerve are also reservoir sites that are actively under exploration in PAIS.
Very important. And so I'd like to talk more about the immune system and reactivating dormant or latent viruses in the body. What are the implications for patients seeking care if you were treating someone, or if you could give advice to someone who's treating someone and they would like to order a test, or what would you test for in terms of potential reactivated viruses in PAIS?
Yeah, so our research has shown, for example, that there's a subset of long COVID patients that have evidence of recent reactivation of Epstein-Barr virus, which is a member of the herpes virus family. And these people, it's not uniformly reactivating in everyone, but it's a subset, and it's enriched in women with long COVID. And same kind of results have been reported by at least 2 other groups. And the Jim Heath's group in Seattle has shown that EBV reactivation at the time of acute COVID infection is one of the 4 predictive factors for developing long COVID. So it's not only that there is reactivation, but there may be some causal link associated with the development of long COVID. So what we currently don't know is whether this reactivated virus itself is causing the symptoms, or whether it's a combination of the reactivation along with something else like the SARS-CoV-2 reservoir that's causing the totality of the symptoms. So to that end, we are developing animal models to be able to identify whether there's a causality in EBV reactivation for some of the symptoms, and whether treating EBV is something that would benefit patients. Currently, we don't know this yet. Some of us, including Amy, we are planning to test this in a randomized clinical trial in the future. Currently, I would say that, doctors who are being consulted by patients about this, there are some laboratory tests that they can order to see if there's a recent reactivation of EBV. This is mostly based on the antibody test that they can order and see if that is indeed happening in the patients. At least this knowledge might help the doctor and the patients come to some kind of therapeutic intervention in the future. Knowledge is very important for both the patient and the doctor. So that's one thing that one could do. However, there's nothing that's immediately actionable by knowing this result at this point.
Yes, and thank you for that. I think I totally agree. Knowledge is power, and although there may not be an immediate treatment, having that documentation in the patient record could be very helpful for them down the line. But would you say in a perfect world, during the acute phase of infection, someone would get tested for EBV and you would see if the reactivation was happening in real time?
Yeah, that would be pretty amazing. Because as I said, Dr. Heath's paper showed that those who had viremia, which is really not just reactivation, but having EBV in blood circulation, it was one of the 4 risk anticipating factor for long COVID. So yes, knowledge is power, and by knowing whether you are having viremia during the acute phase of COVID is one of those knowledges that may be useful in the future. There's a lot of other things that I would love to know about personally. If I get COVID, here are the things that I'd like to measure. But these things, of course, insurance may not cover all of these.
Yes, I'm hoping that we can be more accommodating with the insurance. But you touched on something that was very fascinating, and that was the sex differences. I am actually reading your preprint of your sex differences paper, but sex differences in symptomology and immune profiles of long COVID. Extremely fascinating. I would love to know more about your findings between male and female patients, and some of the important things that our medical students should know, especially when they have people walking into their office as they're treating people. What pieces of knowledge can you offer to these students?
Oh, thank you for that. Yeah, we're very delighted. We finally posted a medRxiv article, which you're reading. Thank you. And this is a collaboration with Dr. David Petrino at the Mount Sinai Core. So especially very meaningful to speak on this platform. But what we did collectively, we studied immune signatures of people with or without long COVID. And sort of these people are on average about 400 plus or minus days from the initial infection. And looking at their immune signatures, we noticed that not all the symptoms, for example, are equally reported by male and female patients. So, for instance, there are some things that are very common, like fatigue and other issues, whereas others, like hair loss for women, was the most sexually dimorphic symptoms that's reported. That's higher in women compared to men, and sexual dysfunction, on the other hand, was more common in males than females. And so, by looking at the symptoms and organ involvement alone, we already knew that there was a significant sex differences in the tissue involvement of these symptoms. And then we went on to do a deeper dive in the immune responses in these patients. And we found that there are key immune differences, one of which I already mentioned is the EBV reactivation happening mostly in women with long COVID. And then also these women with long COVID had more signatures of exhausted T cells. These are something that Amy had already alluded to. T cells that are seeing the antigen and aren't able to kind of clear these antigens, they become exhausted. So we see evidence of those mostly in females with long COVID. On the other hand, males with long COVID had elevated NK cells and some cytokines that are very unique from those found in females. And then what's also further interesting, when we looked at different hormones that are associated with disease status, we found that testosterone levels was a negative predictor of long COVID status and disease severity. So what this means is that women and men with long COVID, their testosterone levels, the lower the testosterone level, the worse off their disease was. And this was really interesting because testosterone has been mostly studied in men because obviously men have much higher levels of this hormone than women. However, testosterone is an important hormone that regulates many physiological function in women as well. And we're seeing reduced levels of this sex hormone in women with long COVID. And that reduced level is really predictive of their long COVID status as well as organ involvement. So all in all, we found many sort of hormonal as well as immunological and symptomatic differences in males and females with long COVID. And hopefully this will lead to some sort of insights and therapeutic strategies that we can deliver to men and women, perhaps different kinds of medicines.
So I was reading through the paper and I was very intrigued, especially on that last note. Where do you go from here? This is so intriguing. What kind of therapeutics do you believe would be offered? And would they be controversial? On
the Twitter, after I posted this, of course, there were lots of ideas being, suggested, which is wonderful. But you're right. I mean, in fact, I just want to give you a small backstory of how this study even began. I was contacted by a mother of a child undergoing sex-affirming treatment. A trans sex-affirming treatment for her child who had long COVID. And so when the child was receiving testosterone injections, the symptoms really alleviated, a dramatic improvement. So when the mother contacted me about this, we thought, oh, well, we ought to look at the sex hormones and see if they're really different in people with long COVID. And there it is. We see a huge difference there. And so, again, future clinical trials are needed to really understand what it is that we can provide, but potentially a low-dose hormone therapy for people who have this very low-level testosterone might make sense. Again, this is something that is still in a hypothetical stage, but that's sort of one implication of the study.
That's very interesting. And just as an aside, I've been hearing so much about women's health and how many of us neglect getting our hormone levels checked, and we don't know our hormone levels. And I just think that that is helpful information, especially in light of these types of studies. So I will keep that in the back of my head.
Absolutely. I think you're right. I mean, I wish I had a clinical lab, attached to my house. I do.
Exactly.
One thing, Raven, that's interesting to me on the side of as a microbiologist looking at the sex differences is that there are nuclear receptors, which are hubs that control hormone expression in the human body. So alpha thyroid receptor, estrogen receptors, androgen receptor. And there are some studies that show that pathogen proteins can dysregulate and modulate the signaling of those receptors. There's a really interesting study showing that the SARS-CoV-2 spike protein can directly modulate and dysregulate the activity of estrogen beta as a signaling receptor. So pathogens and their proteins can directly impact hormonal signaling in ways that we should be looking more closely at, because those hormone receptors then sometimes express genes connected to the immune system, and thus really infection is connected to hormone signaling, which is connected to immunity, so all of these should be studied together. And when we think about doing that, that helps us with a clinical picture in which when a patient comes in, future care can hopefully be multifaceted, in which we could potentially address the infection, for example, mitigate a reservoir that could be creating proteins interfering with hormone signaling, while potentially bringing hormone balance up or effectively with hormone therapies and even impacting the immune response from different angles. And I think that's key to the kind of care that's being developed in PAIS, where we think patients are going to need more than one intervention to be able to improve. They're going to need a mix of different interventions that might have to be tailored per the patient.
Absolutely incredible. Thank you. We're going to pivot to Ed. I want to put you in the hot seat a little bit. And I want to ask you, what are some of the biggest misconceptions about Lyme that you can think of that maybe some of our medical students might have heard in passing?
So our research, which is essentially a institutional review board approved study that we started in collaboration with Chris Woods, an infectious disease doctor at Duke University Medical Center, started just with a single genus of bacteria and a occupationally high-risk group of individuals who are veterinarians, veterinary workers, animal health workers that have exposure to these bacteria all the time. And that is actually, we had done research on Lyme disease in dogs, and interestingly enough, even with tick attachment studies transmitting Borrelia burgdorferi, the vast number of dogs immunologically eliminate the infection as well as we can tell. There's no reservoir, but a subset do go on to develop the same types of pathology that are seen in humans, particularly the arthritis, occasionally myocarditis, and to a lesser extent, well characterized in dogs would be neuroborreliosis. It's the only reason I go back to that background is that Bartonella then became one of the important co-infections in patients with Lyme disease. And more recently, we have focused on the enhanced detection of the genus Babesia in the same subset of patients. And it is very clear now that some people that have Borrelia in their blood, we're still trying to figure out which Borrelias in many instances, have Babesia and Bartonella, or any combination of those three organisms. And I think what we're going to find is Amy's talked about the intestinal microbiome, the oral microbiome, the fact that literally every component of our bodies has a microbiome. The blood increasingly has a microbiome that's consisting of bacteria, viruses, and maybe protozoa and funguses that our immune system deals with on a daily basis. And there's certainly studies to support the fact that we translocate bacteria when we go under anesthesia, for instance. You can translocate bacteria if you aggressively brush your teeth. So the idea that blood is sterile is no longer a realistic possibility. And so, what brought us into essentially entering patients with a diagnosis of chronic Lyme disease, and oftentimes rheumatologic manifestations that were chronic, insidious, progressive, and resulted in, ruining that person's quality of life, was starting with a single genus of bacteria that's completely different than the Borrelias, and now to the point that and both Amy and Akako alluded to this, is you're only as good as your diagnostics. And that's been a major focus for us, is to continue to improve diagnostics to be able to detect DNA, RNA, antigens, protein, anything that might be in a patient's sample. Because, as a veterinary internist, if I know what the target is, at least I've got a chance of directing my therapy there. If I'm dealing with an idiopathic disease, then it's kind of like shooting with a shotgun. I just hope I hit something with a combination of therapies that I've started. So I think diagnostics are critical. I think chronic Lyme disease is essentially long COVID. And I think what we can have as a result of improved molecular and other diagnostic modalities is literally a revolution in our understanding of the microbiome and the pathobiome that causes chronic illnesses.
And Ed, just to clarify that, I think what you mean is that, do you mean partially that Borrelia right now is assumed to be just one of the pathogens that someone can acquire from a tick-borne or vector-borne infection, but it might be helpful for medical professionals to understand that there are other organisms like Bartonella and Babesia that these vectors can also carry? So in patients, there might be more to look at on the front of tick-borne or vector-borne illness than just Borrelia alone?
Absolutely, Amy. I think, again, our publications on Bartonella already support that. Hopefully within the next several months, there'll be publications accepted on Babesia, which, two PhD students and Dr. Ricardo Maggi, who's a PhD microbiologist, has worked with me for a long time, has been working on. And again, in veterinary medicine, we have a very good understanding of Babesia because it infects cows, it infects dogs, it infects cats, it infects horses, and these are all different Babesia species. So we're pretty familiar with Babesia and what it does as an acute disease. We're a little bit familiar with this concept of an animal being infected with Babesia and being chronically infected for months until an unsuspecting veterinarian gives it a vaccine. And our vaccines, for instance, if we use them in a dog, may have 5 different organisms, which means 5 different antigens. And so what we've seen in that setting is analogous to the long COVID story, but just the opposite, where you've got a dog that's chronically infected with Babesia. Outwardly, it's totally healthy. A vaccine's administered, and then within a week, we're seeing it for a life-threatening immune-mediated hemolytic anemia, because all of a sudden, as you alluded to, Amy, that dog starts making antibodies against that Babesia that it's been carrying for a long time and destroys all its erythrocytes. So it's been said by a lot of people. Back in the 60s, the Attorney General of the United States said we knew everything that we needed to know about infectious diseases that just happened to predate HIV, borreliosis, Lyme disease. We didn't know Bartonella existed, and I could go on. So I'll just say what I said earlier for the medical students, that this is an opportunity for literally a revolution in our understanding of a whole spectrum of infections that can be very chronic and insidious and cause disease in their patients.
Thank you, Ed. I would like to touch on something you mentioned about being asymptomatic but still carrying the bacteria. What is the likelihood of someone encountering a tick-borne or vector-borne illness, even if they aren't, let's say, like the quintessential outdoorsy person? Like, where do these pathogens exist, and what is the likelihood that we're carrying them right now?
So, two things I would say, Raven, and one is, although I think microbiomes are of critical importance and deserve a lot of microbiological attention, I'm still an internist by training, and I believe that pathobiome, and that a finite group of organisms or situation or diseases can alter that microbiome and ultimately induce the disease in my patient. When I think of this situation, I think of the interaction between the pathobiome, organisms that we're not accustomed to seeing very often or ever. Rocky Mountain spotted fever, for any of us in the South, is a very important disease because it's tick transmitted. When you get it, you get really sick. You're either treated effectively or you die. But if you aren't treated effectively, or if you are treated effectively and recover, you're probably immune for the rest of your life based on experimental studies we've done in animals, as well as the human literature, where there's not any evidence of people getting Rocky Mountain spotted fever more than once. But other organisms, which is a question you asked me, ehrlichiosis. Dogs carry Ehrlichia for years. Babesiosis. Dogs carry Babesia for years. We have tested cats owned by veterinary students for the entire time they're in school, which is 4 years, and they remain bacteremic for 4 years, to a level that we could actually culture it out of their blood repeatedly, sequence it, and say it was the same species and strain. So I think, again, we went from thinking that you had to be an animal health worker or someone that had a lot of occupational risk, a forester, a farmer, to acquire Bartonella. We now think that you probably would have to work very hard to get through life without being infected with one of the now 50-some Bartonella species that have been identified worldwide. So we went from not knowing they existed to thinking only you got to be somewhat at high risk to be, as you alluded to this, to now believing that you really have to work pretty hard to get through your entire life and not being exposed and infected with these organisms.
Thanks, Ed. And I also heard that Bartonella infects and persists in vascular endothelial cells. And so people who are suffering from post-acute infection syndromes that are initiated by Bartonella can experience problems with their blood vessel functions. But Bartonella can also drive a range of neuropsychiatric and neuroinflammatory and nervous system and neuropathy-related symptoms too. We're coming up towards the end of our podcast. I would like to go around and just make sure that you have the opportunity to share something that you believe is important for the medical students to understand about post-acute infection syndromes. Amy, if you can think of anything, even if it's just a summary or fun fact or things that they should know.
Sure. I think the most important thing as a medical student to understand is that a patient with a PAIS, whether the PAIS began with a viral infection, a bacterial infection, or maybe a fungal infection, can come into your office and look totally fine. Because what we know with these patients, and we've been mentioning tissue, we've been mentioning things that are happening, for example, in sites like nerve, those don't manifest sometimes as overt physical deformations or anything that can be seen so obviously. So the first thing to understand as a medical student is that a patient with PAIS can come in and look totally fine, but they could still be incredibly sick. I think the second thing that we really talked about is that some of the top trends that are being identified and further studied in the space are that the pathogen may not clear, it may persist in a reservoir. But again, the technologies that we have right now to find that reservoir are still under development and not really yet available at a clinic in a way that can give you any kind of definitive answer on whether or not someone has cleared an organism like SARS-CoV-2. So you have to be open to the idea and use the patient's symptoms, their history, to potentially infer that something like a persistent reservoir might still be occurring. Then there was the second important trend that Akiko discussed, which is that a new infection could disable or modulate the immune response in a way that allows another latent infection, like an Epstein-Barr virus infection, to reactivate, or that there can be reactivation of latent pathogens in patients with PAIS. Those can differ among patients. So every patient has a different mix of viral or bacterial or other organisms that may fit into that pattern. Again, the testing isn't perfect, but there can be some understanding that people may be carrying maybe not even just one infection, but that there could be a number of different hits in their case, different pathogens that might be impacting their common symptoms. And then I think, as we mentioned, the collective activity of all the organisms in their body can also shift in ways that could be potentially addressable with some therapeutics or some dietary changes. I also think that, as Akiko mentioned, we may be looking at some forms of autoimmunity in patients with PAIS. And one thing to consider there that I think is an interesting area of research moving forward is that in some cases, a protein made by a pathogen can be similar in size and shape to a human receptor or human structure. And so sometimes when the immune system targets a pathogen protein, it can cross-react and also target a human structure receptor, and that's called molecular mimicry. So there is a basis, and that doesn't always have to be the reason why autoimmunity could be occurring, but there's a basis in autoimmunity, which by even infections can be at the root of autoimmune processes. And so all of these patterns fit in together as we move forward to looking at these patients and understanding that there's unlikely to be one PAIS mechanism that accounts for everything in a PAIS patient. What's going to be necessary is going to be listening to the patient, then doing a workup as well as possible and understanding that a mix of different factors may be impacting each case, and working with that patient to begin to try to wear down to the greatest degree possible those different factors that can often result in common symptoms.
Thank you, Amy. Akiko?
Yeah, so Amy did a great job. I'm just going to add a few things about just sort of asking the medical students to be open-minded and, as Amy said, listening to the patients. And so these PAIS have been sort of medically unexplained. And so there are currently no tests that you can order to diagnose these patients. And that's why the dialogue between the patients becomes so important. So even though there are 200 plus symptoms that are reported for long COVID, there are some main symptoms and signs that are typically present in most of these patients, such as exertional intolerance, fatigue, flu-like symptoms like the sickness behavior with fever, muscle pain, feeling sick, as well as neurological and neurocognitive symptoms, and sometimes rheumatologic symptoms of chronic and recurrent joint pain. So when patients present with these sets of, or at least a subset of these sets of symptoms, and you cannot find other causes that can explain it, I would like the medical students to be definitely keeping this PAIS as a possible diagnosis in mind, because that would really help the patients. Often what happens is the patients go into the doctor's office and, because they can't find a marker or some kind of biological changes that they can order from a standard lab test, they're being dismissed as not having any disease or maybe a psychological disease. And this kind of practice needs to change. So I just wanted to emphasize these issues there.
Thank you, Akiko. Ed?
I'm going to repeat what Akiko and Amy said with a somewhat different twist. Again, one of the advantages I have as a veterinarian is I get to treat all the species on the planet except for one. At least my license says that. And I have been amazed at the amount of suffering that many of the people have experienced that we have entered into our institutional review board research study to look at Bartonella, Borrelia, and Babesia. And it's because of the silos that we've kind of created in the practice of medicine that if they have joint pain, they end up with a rheumatologist. If they have neurologic abnormalities, they end up with a neurologist. If they're having autonomic output abnormalities and it's primarily being manifested because they can't swallow or their intestinal tract's not working properly, they might end up with a gastroenterologist. And I can tell you from our studies of sick veterinarians, veterinary technicians, and others that many of them had been to 8 to 10 specialists before they were ever suspected to have an infectious disease, much less being tested for it.
Absolutely. I couldn't agree with you more. And the complexity of post-acute infection syndromes really does demand a multidisciplinary approach and collaborative approach, and a lot of communication, whether it's between the patient and the provider, but also cross-provider communication as well. And so thank you, everyone, for your time. I think today's discussion really illuminated a path forward in understanding and tackling and treating these diseases. And thank you to Dr. Amy Proel, Dr. Akiko Iwasaki, and Dr. Ed Reichwart for your time and your invaluable insights and research. We will see you for the next episode.
Thanks, Raven.
Thanks,
Thanks, everybody.